Hello! Today we continue to work our way through Chapter 8 Multiplication, and we look at 8C, Multiplication Algorithms. We will look at 4 algorithms for doing multiplication. 3 of these are somewhat standard, and the 4th one is a little unusual. And then we'll think about multiplying fractions, and the algorithm for multiplying fractions, and why that algorithm works. I'll take the same number, the same product for each of our examples. So let's see how these work. The standard algorithm, that's probably the one that's most familiar to everyone. How this works, you just take our two numbers, 52, 73, stack them on top of each other, and then starting from the right, I might multiply 3 times 2, I get 6, 3 times 5, I get 15. Now, for 7, I'm going to multiply 7 times 2 and 7 times 5, but first, put a 0 down there. 7 times 2 is 14. Now, 14, I'll put a 1. I'll need to put the 4 down, but that 0 helps me remember that I shift in by 1. 7 times 5 is 35. Add 1 to get 36. Put down the 36. And at this point, I add the results. 6 plus 0, 6. 5 plus 4, 9. 1 plus 6, 7. And then the 3. And there's our answer, 3,796. Let's take a look at a different method. Partial products. So 52 and 73, well 52 is really 50 plus 2, and 73 is really 70 plus 3. What I'll do is take all possible combinations of those two and multiply them together. And it doesn't really matter the order, but it helps to go from largest to smallest. So let's start 50 times 70. I only have to know single-digit multiplication, so 5 times 7 is 35. And then I have 2 zeros, so stick my 2 zeros down there. Now, how about 50 times 3? 50 times 3. 5 times 3 is 15, and I'll put 1 0. So we get 150. Now, how about 2 times 70? 2 times 70. So 2 and 7 is 14, and I'll have 1 0 remaining. And lastly, 2 times 3. 2 times 3 is 6, and the 6 goes on the far right. Now I can just add up all of these results. 6, 5 plus 4 is 9, 7, 3, and we get the same answer as before, 3,796. The lattice method. This is a cool method. Some people do learn this in elementary school. Many people have never seen it before. We set up our product, 52, but instead of putting 73 below it, I make a box, and I'm going to make it too high to fit my 73. If I was multiplying by 731, I'd make my box a little bit longer and just multiply it this way, but I only have 73. At this point, I put some diagonals down. I'll make my diagonals extend past the box just a little bit. And now, start multiplying the numbers. 5 times 7 is 35, so I will put 35 in this box, separating the 3 and the 5. 2 times 7 is 14. 1, 4. 5 times 3 is 15. 1, 5. And 2 times 3 is 6, so the 6 goes in this bottom right box, but I'll put the 6 on the bottom right, and I could put a 0 there if I really want. At this point now, start adding in the down direction, so down left. So I get the 6 here. 4 plus 5 is 9. 5, 1, 1, that's 7. And then 3 is left over. And now I read my results around from top left to bottom right. 3, 7, 9, 6. And there's my answer again. That's pretty cool, isn't it? The last method I want to talk about is Russian peasant multiplication. Sometimes this is just called Russian multiplication or peasant multiplication. I even today saw a site that called this Egyptian multiplication. So there are some different methods. To make things a little bit easier, I'm going to change the problem a little bit. 52 times 17. 52 and 17. On the left, do you remember how we found binary representation of numbers? We divide by 2 if it's even, so 26. But if it's odd, I subtract 1 first and then divide by 2. So 13 minus 1 is 12, and then divide by 2, that gives me a 6. 6 is even, so I can just divide by 2. Oh, 3 is odd, so I need to subtract 1, 2, and divide by 2, 1. So this process is guaranteed to stop at 1, so once I reach 1, I finish. What I do on the right side is I take the number I'm multiplying and I double it. So 17 doubled is 34, doubled is 68, doubled is 136, doubled is 272, and doubled that again. Now, at this point, I'm going to add together some of the numbers on the right side, but I determine that by looking at the left and finding out which ones are odd. So keep the odd. So here's odd, odd, and odd. Now for the evens, whenever I have an even number on the left, cross it out on the right. Even number on the left, cross it out on the right. Even number on the left, cross it out. And I only add the odd ones that remain, the numbers corresponding to the odd ones that remain. So 68 plus 272 plus 544. So 8 plus 2 is 10, plus 4 is 14. I'll carry the 1, write down a 4. So 1 plus 6 is 7, plus 7 is 14, plus 4 is 18. Carry the 1, write down the 8. 1 plus 2 is 3, plus 5 is 8. And there is our answer, 884. And it's pretty remarkable that this should be the answer. What a crazy process, right? I really like to include Russian peasant multiplication for a couple reasons. First of all, it's not like any other kind of multiplication that we've seen before. This opens our eyes to what multiplication can be. Multiplication isn't always just the standard algorithm. There might be some crazy algorithms out there that no one has ever seen before, but could be even a better way of multiplying numbers together. The second reason I like to include Russian peasant multiplication is because, in fact, this really is how computers do multiplication deep down inside in their hardware. This is algorithmically, for a computer, this is the best way of multiplying numbers together. Kind of cool, right? This thing that it's not evident, it's not how we usually think about multiplication, and really, for us, it's not how we would want to do multiplication, but for a computer, this is the way to do it. So there is value in thinking about other ways of multiplying. Okay, let's turn our attention now to multiplying fractions. So why should it be that a times 1 over b is a over b? Well, I like to think about this in terms of repeated addition. Say if I have 3 times 1/7, what does that really mean? The repeated addition model means 1/7 plus 1/7 plus 1/7, and that's 3/7. That seems to make sense. How about this product 1 over a times 1 over b equals a over b? Why should that make sense? Well, we've seen that in our area model. Suppose I have a unit square, so 1 by 1, and I divide this into a regions in the bottom, so I get 1 over a, and I divide this, so a slices, and maybe I divide this into b slices in the other direction, so I get 1 over b. Then I will have a, b squares all together, and the area of one of those will be 1 over ab. We had seen this previously in a problem where we multiplied 1/2 and 1/3 together, and we got 1/6. Okay, so this is just the stuff repeated from the previous slide. In the first case, we can reason out that a times 1 over b is a over b because of the repeated addition model. And in the second case, we can reason out that 1 over a times 1 over b is 1 over ab, and we did this using the area model. Here's really what we're after, our multiplication algorithm for fractions. Why is it that a over b times c over d equals ab over cd? So, I first of all convert the a over b and the c over d into different fractions using part 1. So a over b is a times 1 over b. C over d is the same as c times 1 over d. Now I can rearrange terms because of commutativity, AC times 1 over B times 1 over D. And now the rule number 2 tells me how to multiply these two numbers together. That is 1 over BD. But then rule number 1 tells me how to multiply a number times 1 over a fraction, and that is, how to multiply a number times 1 over another number, and that's AC over BD. And there it is. This tells us how to multiply two fractions together. So our algorithm for multiplying fractions says multiply across the top and multiply across the bottom. And here is a little proof showing us why that is the correct algorithm for multiplying fractions. All right, give the homework problems a try, complete the worksheet, check your answers, and I look forward to seeing your work a little bit later.